fast enough, we can overcome it. So how many minutes you need actually?
I'm not sure. We'll see. Maybe, I think I'll finish in 14, 15 minutes. 10 slides.
After that first slide is this, and last slide is the.
Thank you.
Our next speaker is Samprit, and he will be talking about analytic minimal subfields of elliptic curves.
Thank you, and thanks to the organizers for inviting me to give a talk with such an esteemed audience. I'll be talking about analytic minimal subfields, which is a recent paper that I published under the name of Minimal Subfields of Elliptic Curves. So let K be a number field and let E be an elliptic curve defined over K. We know that the Model-Well theorem tells us that the K rational points of E is finitely generated. R is the rank of the elliptic curve. Kumar and Amir studied this very interesting object associated with it. So it's called a minimal subfield. If you have a finite extension f over k, we are concerned about how far down can you push without changing the rank. So m, rank of E of m is same as the rank of E of f of the top field, and m is minimal. So they introduce this object and they show that it exists, such a field exists, it is unique. If you start with a Galois extension f over k, then the minimal subfield is a Galois extension. And they give explicit description when the rank is small, 1, 2, or 3, what are the possibilities of the Galois group. Now, in my paper, I also study some algebraic questions, but today I'll focus more on the analytic side of things. So the famous Birch-Swinnerton-Dyer conjecture predicts that the rank is equal to the order of vanishing of the corresponding L function at s equal to 1. So just like the minimal subfield, you can define an analytic minimal subfield in the following way. Suppose you take a 0 of the L function. So omega is a 0 of the L function of the top field. F over k is a finite extension. And then the analytic minimal subfield f omega is defined as, in a very similar way, the order of vanishing is same as the top field. And if there is any other intermediate subfield for which the order is the same, then f omega is contained in k prime. In that sense, it's minimal. So they shows, let me go to the next slide. So from the work of Akbari and Murthy, so they show that the existence of the analytic minimal subfield, in fact, depends on the holomorphy of these twisted L functions. Oops. Yeah, these twisted L functions, where chi is an irreducible character of the Galois group. So it exists only when the extension is Galois, and the twisted L functions are holomorphic at s equal to omega for all irreducible characters. The idea is the following. The idea of the construction is that you look at all those characters chi for which it vanishes at omega, and then you look at their kernel, you take the intersection of all their kernels, let's call that subgroup H omega, then F omega is just given by the fixed field of this subgroup H omega. It's quite natural, but yet quite interesting. Then so as you can see, if we want to work with the analytic minimal subfield, we need to be concerned with when do these twisted L functions when are they holomorphic. So in that regard, they prove two results. Number one, suppose E satisfy the general Taniyama conjecture over K, and F be a solvable Galois extension. Let chi be an irreducible character of the Galois group. Then these twisted L functions are holomorphic at S equal to omega if omega is a simple zero of the L function of the top field, right? And then of course, if they are holomorphic, then in this, under the same assumptions, the analytic minimal subfield exists. Moreover, they show that such an analytic minimal subfield is cyclic extension of K. If omega is a real number, of course, for Burt's BSD, we care about what happens at S equal to 1. So if omega is real, this is in fact degree at most a quadratic extension. F omega over K is at most quadratic. So there are some comments that needs to be made. Firstly, recall the general Taniyama conjecture. It just says that for any number field K, the L function is that of a cuspidal automorphic representation of GL2AK. Now, of course, when K equal to Q, that conjecture is now known. We know modularity due to amazing works of Conrad, Taylor, etc. Secondly, if you go back to the first theorem that they show is reminiscent of an interesting theorem of Stark, right? It's a classical theorem about Dedekind zeta function. If you have F over K is a Galois extension, if zeta F has a simple zero at S equal to S naught, then the Artin L functions are holomorphic. Even the second theorem that they showed is also has a sort of a classical counterpart. There's a classical result of Hilborn and Stark, which says that if beta is a real simple zero of the Dedekind zeta function of the top field, then it's probably coming from either K or a quadratic extension of K, right? So this was kind of what motivated me to look at this, and I thought to myself that maybe I would be able to prove some more elliptic analogs of similar theorems, and maybe I'll apply them to the analytic minimal subfield context. And that's what I do in this part of the paper. So here is a result of Foot and Wells, where they generalize the simple zero to a zero of order up to 2. So the result of Foot and Wells says that if the Dedekind zeta function of the top field has a zero of order less than or equal to 2, then the Artin L functions are in fact holomorphic. So the elliptic analog of that is true. If E over K is an elliptic curve, again, we are stating that K, it satisfies the generalized Taniyama conjecture. So if K is Q, if your elliptic curve is over Q, it's an unconditional theorem. If F is a Galois extension with solvable Galois group, and chi is an irreducible character. Similarly, if we have the L function of the elliptic curve over the top field, if it has a zero of order less than or equal to 2, then all these twisted L functions by irreducible characters are holomorphic. Here is another similar result. This is a result of Foot Murthy. The Murthy is Kumar Murthy, where again, it's sort of the same kind of idea. Rather than looking at the order of 0 to be 1 or 2, those are the two cases we addressed. This generalizes it a little bit more to where the order of vanishing R is P2 minus 2. P2 being the second smallest prime factor of the order of the Galois group. A similar elliptic analog holds as well. If the L function of the elliptic curve vanishes up to the order P2 minus 2, then these twisted L functions are in fact holomorphic. Now, a small remark here, if what we're saying the second smallest prime factor, if the Galois group has only one prime factor, that means it's a p group. So in fact, it is nilpotent. And we know that in nilpotent cases, it's known. And as I started with, if the twisted L functions are holomorphic, then the minimal subfield, the analytic minimal subfield exists. So under the same assumption of these previous two theorems, the analytic minimal subfield exists. Now, if we focus on the case where the order of vanishing is 2, what can we say about the analytic minimal subfield? So here is a result. We can actually describe the Galois group. So suppose the order of vanishing of this L function of the elliptic curve over the top field has a 0 at omega of order 2, then f omega exists, the analytic minimal subfield, and the Galois group is one of the following two. It is either cyclic or dihedral, or the center of the group is isomorphic to Z mod 2Z, and G mod the center is dihedral, A4 or S4. These are the possibilities. Perhaps a more interesting application of this analytic minimal subfield is the next result. So we know that over the rational numbers, the BSD conjecture is known when the order of vanishing is up to 1. Right? It's due to amazing work of Zaghi and Kolivagin. I was able to perhaps very slightly generalize Kolivagin's result. So if E over Q is an elliptic curve and K is a solvable extension, Galois extension, if the rank increases by 1, if rank of E of K is rank of EQ plus 1, then the order of vanishing increases by at least 1. It's bigger than or equal to that plus 1. And for the other way, for the converse, you will need the assumption of this holomorphy of the twisted L functions. If L over Q tensor chi, comma S is holomorphic at S equal to 1 for every reducible character chi, then if the order of vanishing at 1 increases by 1, then the rank increases by at least 1. Now, equality holds if the algebraic and the analytic minimal subfields are equal. We defined analytic, and the very first slide had, that's what we are referring to as the algebraic minimal subfield. A corollary of this theorem is if in fact you, rather than taking K over K as a solvable Galois extension, if you restrict to a quadratic extension, then it's an if and only if. If K over Q is a quadratic extension, then the rank increases by 1, if and only if the order of vanishing increases by 1. And just another small remark, if we assume E has Cm, then this condition of holomorphy in part 2, we can circumvent it. By the way, for these solvable extensions and the second part, I heavily use results of Professor Ramamurthy from the base change and BSD paper and on RTNL functions paper. That's it. Thank you and happy birthday. I'm sorry? No, because so that's the approach when we for solvable extension we know the automorphy of the L function of the top field. So nothing beyond solvable so far. Yes.
Any more questions, comments? If there are none, let's thank the speaker. Our next speaker is Waldschmidt, and we have a few minutes. I think 2 minutes.